Hello, I welcome you all to your own channel. I am Skill Learner. Now, in this video, we will see the momentum equation. As you already know, the momentum equation comes from the Newton's second laws of motion. That means the rate of change of momentum is nothing but the applied force, right? So here we will see the application of momentum equation in the pipe bending, right? So here the momentum equation is what basically it is based on the law of conservation of momentum, or on the momentum principle, means which states that the net force acting on a fluid mass is equal to the change in the momentum of flow per unit time in that durations, right? So whatever the net force is there, that force should equal to the rate of change of momentum. That basically it is the Newton's second laws of motion, or you can say that according to Newton's second laws of motion, that F is equal to ma, that mass into acceleration, and m is equal m into dv by dt, that is rate of change of velocity is nothing but the acceleration, right? So F is equal to d of mv by dt. So while you cross multiply, you'll get the f dt is equal to dmv. As you know, the force into time is nothing but the impulse, and the mass into velocity is nothing but the momentum. So d into mv is nothing but the change of momentum. So this equation is nothing but the it is the impulse momentum equation. All right, so this f dt is equal to dmv is known as the impulse momentum equation. So this is next we will see that we have a pipe is there, right? So far, whenever we apply the Bernoulli's equations, and then we have to find out the pressure head or kinetic head or potential head. So either means either the pipe is your horizontal or it's a vertical, right? What if the pipe is bended, right? So whenever the pipe is bended, it means that you have to find out the component, right? Means the force component you have to find out basically on the x-axis as well as on the y-axis, right? So we will see first the theoretical concept of the force exerted by a flowing fluid on a pipe bend. Means you have a pipe is there, and then that pipe is bended with certain angle, right? And through that pipe the fluid is flowing. So how much force is exerted in that case we are going to see. So here we have that the impulse momentum equation is used to determine the resultant force exerted by a flowing fluid on a pipe bend, right? So now we consider one pipe of having two sections, that section 1 and 2, and the pipe is bended, right? It's not normal pipe. So let v1 is the velocity flow at section 1, and p1 is the pressure intensity at section 1, and a1 is the cross-sectional area at section 1. And similarly you can say v2, p2, a2 are the corresponding values at section 2. Now here we have a schematic layout. As I told you that the pipe is not normal, so this you can see that section 1, this pipe is up to here, it is horizontal, and from this point it is bended with certain inclination which is theta, right? So as it is bended, so up to here the force or velocity and pressure, force, velocity and all those things are completely horizontal. Why? Because the pipe is exactly horizontal. Now when it is here at this point, the pipe is not exactly neither it is horizontal nor it is vertical, it is inclined with certain angle, right? So whatever the velocity, pressure, force and all those things will be also inclined. So from this point you need to find out the component, right? So as I show that force exerted on x-axis, that is fx is the force component of forces in x-axis, and fy is the y-axis component, right? Now so here that section 1 we have considered, and at this point the section 2 is considered, right? So the pressure forces p1 and a1 is why? Because the fluid is flowing in like this. So while the p2 a2 will be the counter force which acting opposite directions, right? So here you can say the velocity is v1, and here the velocity is v2, which is inclined with an angle of theta, right? So we have to find out the component of this velocity on horizontal or you can say on x-axis, which is v2 cos theta, and on y-axis it is v2 sine theta. All right, so here additionally we have shown that as the pressure force is countering this P2A2 in the opposite direction to this P1A1, so it's P2A2 cos theta is the horizontal component or force exerted in the x direction, and P2A2 sine theta is the force exerted in the y direction. All right, so now when we apply the momentum equation in x and y direction, and later on we have to use the resultant equation and then find out the force exerted by the fluid on a pipe bending, right? So first of all, what we will do that you draw this schematic diagram, right, and then follow me. So here that you have the momentum equation in x direction. So momentum equation, just now we see that the net force acting on a fluid in the direction of x is equal to what? That rate of change of momentum in x direction. As we say that x direction, why? Because first we are applying the momentum equation in x direction, right? So the momentum equation is nothing but the net force acting on a fluid in the direction of x is equal to rate of change of momentum in x direction. So net force acting on the fluid in the x direction is nothing but let me show you again this pipe bended, that is P1A1 is acting in the positive x direction, and as I told you that this P2A2 is countering this, right? So while you get the component of this P2A2 in x direction, it will show on the left, so it will be minus P2A2 cos theta, and also you have a fx, right? Now because this fx has to be acting the negative x direction, right? And then that is the net force on a pipe in x direction, right? That should be equal to the rate of change of momentum. That rate of change of momentum is nothing but the mass into change in velocity, or you can say the final velocity minus initial velocity, right? So here that mass flow rate is nothing but the density into discharge, or you can say the rho AV, right? And the final velocities of in this flow that is v2 cos theta, and the final initial velocity is v1. All right, so here we go that this is what you have a P1A1 which is in the x direction, positive x direction, minus P2A2 cos theta which is negative x direction, and fx the force exerted in the x direction is minus fx, and then that is equal to rate of change of momentum in x direction, means density into discharge into final velocities minus initial velocity. Or you can write this rho q is equal to rho AV also. As you know, the discharge is nothing but the area into velocity. All right, so rho q into v2 cos theta minus v1. So on simplification further, let me show you that fx is equal to what? That we want the fx only, right? Because we have to find out the resultant, right? So this term will come to this side, and fx you bring it this side, right? So this is very simple, that rho q v1 minus v2 cos theta plus v1a1 minus p2a2 cos theta. As you're bringing this side, so this v2 will become minus and this will become plus, so you can write v1 earlier and v2 later on. Okay, so let's say this is the equation 1, is simple algebra, right? Now we need to find out the force. The same way we are going to find out the momentum equation in y direction, right? So momentum equation in y direction is what? That net force acting on fluid in the direction of y is equal to rate of change of momentum in y direction. So as you know that here only I'll show you that the section 1 is having pipe is horizontal. We are finding the y direction, right? So we have a zero forces. P1A1 is not valid here, so we can write 0, right? And you have this is what you can say P2A2 sine theta, right? It will goes negative downward directions, right? And you have a minus fy. All right, and also we don't have a initial velocity on in y direction. Why? Because initially the pipe is horizontal, so there is no vertical forces and velocity at all. Okay, now so here again you can say follow this, that Similarly, you can write the momentum equation in y direction is nothing but that is a net force acting in y direction is equal to rate of change of momentum in y direction. That as the pipe is initially the pipe is horizontal, so no horizontal vertical forces, right? And P2A2 sine theta minus Fy is equal to density into discharge, and this is V2 sine theta, final velocities minus initial velocity, that is 0. Why? Because initially the pipe is horizontal, so no vertical velocities, right? So on simplification, this Fy will become rho q minus V2 sine theta minus P2A2 sine theta is equation 2. Now as you got the resultant that force exerted in x and y direction, so you need to find out the resultant forces that are Fr is equal to root over of Fx square plus Fy square. So this is how we can find out the force exerted by the fluid flow in a pipe bending, right? First of all, you have to find out the Fx, and then you have to find out the Fy, and then put it into this equation. You'll get the answer, right? So this simple mechanics, as you know. And then if you have to find out the angle made by the resultant force with the horizontal direction, then this is the tan theta is equal to Fy by Fx. As these are the theoretical discussion we have done so far, now I'll show you one a work example, so that it will be quite easy for you to implement it on your working example, right? So here we have one problem. Let's see that problem. Read and write down that a 45-degree reducing bend is connected in a pipe line, the diameter at inlet and outlet, the bending being 600 mm and 300 mm. Find the force exerted by water on the bend if the intensity of pressure at inlet to the bend is 8.829 Newton per centimeter square, and the rate of flow of water is 600 liter per second. It's quite easy. That the pipe is there, that pipe is bended at 45-degree angle, right? So it's having two diameters given, that is at inlet and outlet, which is 600 mm and 300 mm. Then the pressure at the inlet is given 8.829 Newton per centimeter square. You don't have a pressure at inlet 2, so first of all you have to find out the pressure at inlet 2. For finding the pressure at inlet 2, we can apply the Bernoulli's equations, right? As well as we don't have a velocities of fluid flow at 1 and 2, so by using the continuity equation we can find, or by using the discharge formula you can find the velocities at 1 and 2, right? And then simply say substitute into the equation and get the answer. So let's start. So here I'll show you that first of all we will write on the given data that here we go, solution, right? So this is your given theta is equal to 45-degree, right? And d1 is equal to, I'm writing this short small letter, 600 mm, which is nothing but the 0.6 meter, and this is the d2 is equal to 300 mm, right? Which is nothing but the 0.3 meter. All right, so here we can find out the a1, that is pi by 4 into d1 square means 0.6 whole square, which is the 0. See, you can cross check this solution whether it is correct or not, right? So a2 is equal to just hold on, so please write down this, a2 is equal to pi by 4 into 0.3 whole square. Simply you can, this circular pipe is there, so it is nothing but the 0.07068 meter square. All right, the pressure at inlet is given that P1 is equal to 8.829 Newton per centimeter square. So you have to find out, means convert this into meter square, so it will be 8.829 into 10 to the power 4 Newton per meter square. Okay, now so Q is equal to what we have, that is 600 liter per sec, 600 liter per sec, which is 0.6 meter cube per second. Okay, now so first of all we have to find out the v1 and v2 to get that p2. Why? Because for finding the p2 we will apply the Bernoulli's equation. Okay, so here you know q is equal to a1 v1 is equal to a2 v2. All right, so one by one you can find v1 is equal to q by a1, and uh, so here it is what 0.6 by a1 is nothing but the 0.2827, which is 2.122 meter per sec. All right, so similarly you can find out the v2, that v2 is equal to, directly can I write q by a2 is equal to 0.6 by 0.07068. Okay, now so this is what you have, a 8.488 meter per second. Now we can apply the Bernoulli's equation at section 1 and 2 to get the p2, right? So here we go, that you can say the apply Bernoulli's equation, Bernoulli's equation at 1 and 2. All right, so now Bernoulli's equation is what you know. This is, we just assume the fluid is ideal. Why? Because losses is not mentioned in the question, right? If the losses is mentioned, you have to find out that you need to apply the real fluid, Bernoulli's equation for the real fluid, right? So just p1 by rho g plus v1 is squared by 2g plus z1 is equal to which is p2 by rho g plus v2 is squared by 2g plus z2. There's no datum head and all those things, right? So you can just say that z1 is equal to z2, so this and this will get cancelled, right? So basically we have to find out the p2 by rho g, right? So this is what, just bring this v2 squared by 2g to this side, you'll get the p2 by rho g, right? So can you write like this, that I'll just show you that what I'm going to do, that p1 by rho g plus v1 is squared by 2g minus v2 squared by 2g. Okay, so this is equal to p2 by rho g. All right, right. So now you just simplify this p2 by rho g. You have a p1, density is 1000, gravity is or you can let's they get cancel this g, right? So let's comment this and cancel them. So simply you can got the p2 is equal to rho into this hole. All right, so shall I write down the direct answers? That just p1 is equal to 8.829 into 10 to the power 4 by 1000, v1 is square, v1 you got the 2.122 by 2 plus minus 8.488 is equal to p2 by 1000. So you can cross multiply and get that answer, right? So now here, that let's just think that I hope that you can understand and you can easily find the p2, right? There is no issue. So here we can write that p2 is equal to which is what, 5.45 into 10 to the power of 4 Newton per meter square. So as we got the pressure at intensity at section 2, now you can apply means find out the force force on the bent pipe in x and y directions, right? So we can say forces in a pipe, in a bent pipe, on a bent pipe in x and y directions. All right, x and y direction. So first I'm finding the forces in x direction, that is fx is equal to, just now you have seen that the rho q into v1 minus v2 cos theta, okay, plus p1 a1 minus p2 a2 cos theta. Okay, so all the values you have just put that on those data, that is rho is equal to 1000 into discharge is 0.6, and this v1 is nothing but the 2.122 minus 8.488 cos 45 degrees, that pipe is bended with the 45 degrees, plus p1 a1, that is it is given 8.829, okay, 8.829 into 10 to the power of 4, and it cross simply means this is continuation. Into A1 is you have a 0.2827, and this is minus P2, just now you calculated, that is 5.45 into 10 to the power of 4 into 0.07068 into cos 45. All right, so just simplify this and you get the fx. Okay, so it's quite simple that if you understood this, how to find out the forces in x direction. It is simple mechanics, right? So how we are finding the component and all those things. All right, so fx we got, this is 19911.4 Newton. Okay, so similarly that you can write on this fy also. Let's say it is here fy is equal to we have a rho q, okay, minus v2 sine theta, and this is minus p2 a2 sine theta. We don't have a pressure, force and a velocity in section y and y, because initially the pipe is horizontal, right? So we don't have a vertical forces and all those things. So this is 1000 into discharge is nothing but 0.6 minus v2 is, we got something 8.488 into sine 45 minus P2 is nothing but we have a 5.45 into 10 to the power of 4, and A2 is 0.7068 P2A2, and this is sine 45. Okay, sine 45. Very carefully you have to check, right, whether maybe there is a little bit of mistake, then this can wrong the answers, right? So on simplification we'll get the minus 6322.2 Newton. This is our fy. All right, now we can find out the resultant of forces, or you can say the net force also. So resultant of forces, right? So resultant of forces, that is fr is equal to root over of fx squared plus fy squared. So it is just simplification you have to do. That fx you got that 19911.4 whole square plus 6322.2 whole square. Actually it is minus, so while you do the squaring it will become plus, right? So it's not a too big work, right? 20890.9 Newton. So this is how you will solve the problem from the pipe bending. Okay, so this is all about the today class. Thank you.